Thank you, sir. So, hello everyone. So, myself is Raghavendra Ramachandra. I am from Norwegian University of Science and Technology. So, in this work, we are trying to explore the complementary information that are presented by the multispectral imaging, especially to address the phase presentation attack detection. So, word presentation attack detection is in a very common term, it is an anti-spoofing. So, idea is like if you are using a biometric system, then probably someone take your face and then they can generate an artifact and they can present it to your biometric system so that they can get an illegal access to your biometric system. So our idea here is like when we use the multispectral imaging, so we are going to get several bands, and obviously each of these bands are complementary in terms of the reflection characteristics. So depending on the type of the presentation artifact or the presentation attack instrument we have, so the reflective characteristics varies for each of these instruments. So once we have this multispectral imaging, so our idea is to see whether combining at the imaging level versus combining at the very end. That means that the early information and the late information. So which one is giving the better performance in terms of detecting these kind of attacks? So this work is in collaboration with the University of Goa as well as a company in Norway. So of course the first author could not step in, so I am just replacing him for this presentation. So, well, the standard outline. So I start with a quick introduction, then we discuss about our contribution, and then some information about the built-in, because the sensor what we have used is a very low-cost sensor. So it's a kind of custom-made sensor. So very few information on that. And then we discuss about the database, what you have collected. This database is also publicly made available so that any researchers who are interested, they can make use of this. And the simple methodology, what we are used to do the combination at the image level as well as at the score level will be discussed. And then we have experimental results and conclusion. So the person verification using face is the most convenient way. So I believe like we all are used to for this face verification system when we open our smartphone. So if you have your smartphone with your face biometrics, obviously by looking into your smartphone, you can unlock your smartphone. Similarly, like I believe like most of you Indians, you are all enrolled to the Aadhaar card. So in the Aadhaar card also like you have a face biometrics as a preliminary or the primary identifier. So that means that so whenever this face biometric system works, it assumes that your face is already present in the system. That means that the biometric system already knows who you are. And then once you come for the verification, it will capture the image and then it will compare with what it already has. So this is like one-to-one verification. So we normally call this as verification system. The face biometric system compared to the fingerprint, iris, or any other physiological or behavioral biometrics is very popular because of the user convenience, and it can be easily integratable, and it can scale the application with a low cost at the very low cost. So that's the main reason why the face recognition system is more popular. And then nowadays, with the invention or evolving of the deep learning techniques, especially with the face verification perspective, so there are several challenges that are associated with the normal face recognition system. The decade before has been now solved, especially for the constraint condition. So as the face recognition systems go more accurate, the vulnerability of those systems for low-cost presentation attacks or the spoofing instruments have also become very, very common. For example, as you can see here, the upper row represent the bona fide and the lower row represent different kind of presentation attack instrument that one can generate. So for instance, you can take this image, you can just print this image and present it in front of your biometric system. And with today's technology for the face recognition system, all the images in the bottom will get verified with very high confidence with the biometric system. So this is the reason why we need to develop a presentation attack detection system where it can automatically classify the bona fide versus presentation attacks. And nowadays, with the very nice development in the presentation attack instrument, especially in the mask artifacts, where one can generate a 3D custom mask. So basically, these kind of masks are very cost effective, meaning that like with $30, you just upload your 3D face to the web page, and then within 2 days, you are going to get this mask for $30 at your home. So this is very cost effective. So that means that like anyone without any knowledge about the biometric system can generate these kind of instruments and try to attack the biometric system. So when we try to address the vulnerability issues, so basically like when we look into the literature and we see that like most of these techniques are based on the handcrafted and deep learning. So when I refer to the handcrafted, so these are basically a texture based method. So given the image, we try to extract the textures. because what is the underlying assumption here is like when we print the photographs, it has a dotted pattern. So if we can capture the dotted patterns which are not present in the bona fide, obviously we can detect this kind of attack. So that's the underlying motivation for the handcrafted features, where everyone try to use the local binary patterns and its variants together with the frequency information to identify these kind of attacks. So especially when we look into the sensor perspective of this face presentation attack detection, majority of the work as of today is based on the visible spectrum. So one reason for this is because of the scaling of the biometric technology across the smartphones, except the Apple, which is trying to use the Face ID, which has both near infrared and the face part, and other most of these low cost smartphone sensing are based on the visible spectrum. So as we are depending on the visible spectrum, the problem of detecting this presentation attack also escalates. So as a result, so very few researchers are coming and they're trying to explore the use of this multispectral. So among them, the use of infrared sensor and the SWIR sensors are quite popular in the domain. But however, using those sensors only to perform the presentation attack, forgetting about the verification, is very cost effective. And today we are going to scale this kind of application for the low cost application, but it is really costly to have one sensor which only looks for presentation attack while discarding the verification. The one way to address this problem is by using a multispectral sensing, where you also have a visible band where you can use that for the verification. Together with you also have the infrared band that you can use it for the presentation. So this is a kind of compromise we try to play here. So this is the example of the images that we are trying to capture with our custom sensor. So we have in frequency, we're starting from 530 nanometer till 1000 nanometers. We sample it at 50 nanometers at a scale to reduce the redundancy in the information. So, well, the main contributions of our work is like we try to explore the multispectral imaging, especially in visible and near infrared, without compromising the verification performance and the attack performance. That's the main objective. And then we have a qualitative comparison with image fusion, that is the early fusion, and the score fusion, which is the late fusion. So we need to see like where exactly we can identify the system, where exactly we can identify the attacks more easily and more accurately and more generalizable format. And of course, we also introduced a new database with this paper, so which is having more than 61,000 samples. So this is a custom-based sensor. So these are based on the filters. So we have like 9 different filters, and these filters are mounted on the wheel, and this wheel is automated so that it will automatically rotate on a click, and then we capture different images in a single click at different spectral frequencies or wavelength. So in this work, we are going to capture about 9 nanolines from VIS to NIR. So these are the different kind of presentation attack artifacts that we are trying to evaluate in this work. So we have like 2 different print artifacts. So one is on the laser printer, other one is on the inkjet printer. So the quality of the print also varies. And we have used 4 different types of display artifacts. So we used from low cost Samsung Galaxy S8 smartphone as a display until the Apple iMac, which is having a retina display. The quality of the display attacks are very high. So obviously the vulnerability is very high. And then we use 2 different kind of masks. The one is the rigid color 3D mask, and the other one is the white 3D mask. The only difference here is the color. The one is having a color, other one is not having a color, but more or less the material is more or less the same. So in overall, like this is the statistical distribution of number of samples that we have when we consider the bona fide. So we have like 145 subjects who are unique subjects who are collected in 2 different sessions, and each session is having a duration of more than 1 week. And for each session, we have 5 samples, and every sample has 9 bands. So this is the variability we try to have. And then for every subject, we have like 2 different kind of print artifacts and 4 different types of display attacks and 2 different types of masks. So when it comes to masks, it is very costly to have 145 masks for every subject. So we randomly sampled 18 subjects, and then we constructed a mask database for only few subset of the subjects. Well, so these are the examples like how we can visualize the image with respect to the bona fide presentation as well as the different presentation attacks. So if you see here the print attacks, when this print attacks goes towards the near infrared band, we can see that the information varies a lot. That means that it lacks the texture information, and the artifact is prominent, especially in the near infrared. And once we look into the display attack, the more particularly because these displays are visible only in the visible band, obviously you cannot see it in the near infrared. You can see that it is more or less the dot. So this is the advantage of using the complementary information from the multispectral, where the inherent characteristics of the sensor itself is useful for detecting these kind of attacks. So this is the overall system that we have proposed. So we have different spectral bands, and with respect to the spectral bands, we combine them to have one single image, and then we do the feature extraction. And this work, the feature extraction is from the LBP, and then we just pass it to the SVM, and then this is a binary classifier, and then we try to do the accepted or the rejection. That means that whether the attack is detected or not. So when it comes to the image fusion, so we try to use like the two-level discrete wavelet transform. And when it comes to the score level fusion, we simply use the sum rule from all 9 different bands. So to perform the experiments, we partition the dataset as training, development, and testing. So training is used only for training the system. The development set, we try to use it only for fine-tuning the parameters and fix the threshold for the detection. And then finally, we have the testing set, which is used only for testing and reporting the performance. So here we can see that, like with respect to the score fusion, so here we see the detection equal error rate. So when we measure the performance, we have 2 parameters here. One is called BPCR, other one is called APCR. BPCR is bona fide presentation classification error rate. That means that like how many bona fides are classified as attacks. So this is an error. So lower the value is better is the performance. As you see here, like in most of these generalizable experiments, that means that we try to, for example, like if we have 4 different kind of PIs, so we try to train 3 PIs, and then we try to test the last PI, which is not a part of training PI. That means that our system, which is trained, is not aware of the testing PI. So this is called as an unseen attack scenarios. Under these scenarios, we see that except in the one case of display artifact 2, in most of the cases, the performance is very nice at the score level. But however, when we do the image fusion, the performance did not change that much. That means that compared to the score level, the performance is highly degraded, especially with the sensor level fusion. So this concludes that like at the sensor level, even though we have more information, but since we are trying to compress all these 9 bands into the one single band, obviously the information is not enough to identify the presentation attack detection. So this is just a box plot to have a better visualization of the results. We see that like in the generalization experiments, the print attack and mask attack and display attacks are easy to detect. And even the print attacks with artifact 1 is also quite easy to detect. And however, the display attack 4 is quite challenging still to identify. So as a conclusion, so in this paper, we investigated both early fusion and the late fusion. And together we also proposed a new data set that can be used for further research. And we benchmark these results with a very nice protocol, meaning that like we have training, development, and testing. And all these experiments protocols are designed to evaluate more particularly on the unseen attacks where the system is not aware of what kind of attack is coming in the testing set. So with this, I would like to conclude my presentation. If you have any questions, I'm happy to answer. Thank you.